Now using these closure properties, I want to find out the candidate key. Let us say this is the table. Table is containing 4 attributes and these are the functional dependencies given. A determines B, B determines C, C determines D and D determines A. These are the functional dependencies. Now my aim is to find out what are all the candidate keys on this table. The reason is I will find out the candidate key and then make one of them as the primary key, right? So how can I find it out? Now what is a candidate key is, uh, given an attribute, you should be able to uniquely determine all the other attributes of the table, then it is going to be a candidate key in this definition, right? So now how many candidate keys can be possible, or how many elements or how many candidate keys I should test, in the sense, if I have 4 attributes, how many total candidate keys can be possible? See this, if I have 4 attributes, let us say if I have 2 attributes A and B, right, and how many candidate keys can I get? One is A, maybe other is B and other is AB, isn't it? Similarly, if I have 3 attributes A, B, C, then how many attributes, how many candidate keys might be possible? I'm not saying that everything is going to be a candidate key, but how many combinations or possibilities are there? A can be a candidate key, B, C can be a candidate key, AB can be a candidate key, BC can be a candidate key, right? CA can be a candidate key, or ABC can be candidate key. So here I got 3 and here I got 7, isn't it? So in general, what is this? Given this set, what is this? This is nothing but set of all subsets except one element, isn't it? What is that element? The null element, right? So except null, this is the set of all subsets, right? Therefore if I have n elements, which means if I have a1, a2, so on an, right, how many candidate keys might be possible, right, totally? So it could be 2 power n is the total number of subsets possible from this, out of which you should always take out that null cannot be a candidate key, right? Therefore 2 power n minus 1 candidate keys will be there. So I might have to test each one of them and see whether it is really a candidate key or not, right? Okay, and then one more thing is, okay, let's see this example and we shall explore it, right? So for this, coming to this example, how many candidate keys will be there? 2 power 4 minus 1, which means 15 candidate keys will be there. So should I examine all the 15 combinations, or can I rule out some of them? It turns out that we can rule out some of them. So just for the sake of this example, I'm just trying to do it. We are not going to do this procedure in all the examples. Just for this example we shall see it. Okay, it is not required, so don't worry, there are shortcuts also, we shall see them, but just for you to understand the concept, I want to do it. Okay, now for this particular table, is there a guarantee that at least one of these combinations turn out to be a candidate key? There is definitely a guarantee. And what is that candidate key? If you don't find any candidate key, you take the combination of all the attributes and that is supposed to be a candidate key, in case if you don't find anything else to be a candidate key. How is it possible? Because we already have the rule that in a table no two tuples can have the same values in all the attributes. Therefore, by the definition of relation itself, the table itself, a relational database, we have this constraint that if you take the table all the attributes, you will definitely get that as candidate key, in case if you don't find any other candidate key. Got it? Therefore there is definitely a guarantee that if you don't find any candidate key, set of all attributes is going to be the candidate key. Fine. Now how many candidate keys are there for this example? 15. Now I want to see, out of all these 15 possibilities, which of them are really candidate keys, right? So how can I find it out is, first there is this is a candidate key of length 4. Now I want to find out the candidate key of length 3, ABC, right, or ACD, or ABD, or BCD. These are the candidate keys which are possible of length 4. Now I want to see the possible candidate keys of length 2, AB, BC, CD, right, and DA, right, and AC, AD, oh AD is over, right, so AB is over, AC is over, AD is over, AB, AC, AD is over, and then BC, BD, BC is over, BD is not over, BD, and then CD. Let me check. 1 2 3 4 5 6 7. I'm supposed to get only 6. 4C2 is 6. CD is repeated here. Okay, fine. So 6, right? So here I got 1, and here I got 4, and here I got 6, right? So how many is this? 11 I got. And what about the candidate keys of size 1? So A, B, C, D, right? These are the candidate keys of size 1. So 4, isn't it? So I got all 15. Now I have to test each one whether it is going to be a candidate key or not. Now tell me from which order should I start? Which means, should I start from here searching for the candidate key, or should I start from here? You just think about it. It is better if you start from here. If you start from here, you might have to do lot of searches. If you start from here, you will have to do only few searches. The reason is, see, if A turns out to be a candidate key, I'm just assuming, okay, if A turns out to be a candidate key, then what happens is, anything which contains A will not be a candidate key, that will be a super key, isn't it? So candidate key is minimal. Now if you say that A is a candidate key, you cannot say AB is a candidate key, because AB has to be minimal. If you remove B, you can still get a better candidate key, better, minimal, right? Therefore, if A is a candidate key, no superset is going to be candidate key. Therefore, if you search for this one and if you find that this one is a candidate key, then you can rule out many things, right? So you can rule out everything that is containing A. Maybe you can rule out this, right? And then you can rule out this, and you can rule out this. Therefore, see this, how many have dropped out, right? So in case if you find out B, you can rule out many things, right? That is how you should go. In case if A is not a candidate key, then you might have to observe the things which are not which are like that. So what I mean to say is, it is always better that since a candidate key is a minimal super key, you start with the minimal subsets, which means subsets containing less number of elements, and you just try to verify whether that is a candidate key. If you are lucky, right, you will find it very easily. In case if you are not lucky, you might have to go till here. In that case, you might have to search 2 power n. Therefore, it is going to take order of 2 power n, right, exponential time. But anyway, for most of the cases, you will be lucky. And moreover, second thing is, you need not search all this. In many of the questions, options will be given. By looking at the options, you can test which one is correct. You need not actually derive it. You can check the options and go ahead with this. Now let's see for this one. Now let me see if A is a candidate key or not. How can I find out? Find out A plus. What does A plus give? A, and because of A I got B, because of B I got C, and because of C I got D, right? Therefore A is able to derive all the attributes uniquely. So A is a candidate key, right? And what about B plus? So we get B, and because of B we get C, because of C we get D, and because of D we get A, right? And we got all of them. Therefore B is going to be a candidate key. B is also a possible candidate key, right? What about C plus? So C is going to give D, and because of D I get A, and because of A I get B. I got all of them. Therefore C is also a candidate key. What about D plus? Because of D I get D, and again because of D I get A, and because of A I get B, and because of B I get C. I got all of them, right? Therefore A, B, C, D are going to be candidate keys. We are lucky in this case that we got A, B, C, D as candidate keys. Since we got this A, B, C, D as the candidate keys, none of the above can be candidate keys at all. What is the reason? Because they all contain a combination of this. Got it? So whenever any subset contains a candidate key, then it is going to be a super key. Now what we are interested in is finding out the candidate keys. Therefore, for this particular example, these are all the candidate keys. Got it? Now we shall practice lots of examples with which you will be able to identify this candidate key problem easily, right? Okay,